Thank you so much, Mark, for the introduction, and thanks for having me. I hope everybody's enjoying this winter school very much. So yeah, as Mark mentioned, my name's Donald. I work on the intersection of haptics, 3D printing, and virtual reality. So my background is actually in human-computer interaction. And I joined the HIT Lab in New Zealand in November 2024. Before that, I'm originally from Belgium. I did my PhD in Germany. And then yeah, joining the HIT Lab was kind of the not logical step because the HIT Lab does a bunch of, let's say, immersive technologies and so on. So if you're visiting Adelaide from Europe or from the US, then definitely take the time to kind of hop over and come visit New Zealand. Be happy to host you and show you around the lab. We have kind of five academic staff members that work on very different topics, including VR, AR, applied games, AI, and my focus is on haptics and fabrication. Right? So I want to talk today. I want to talk more about kind of the importance of haptics and how you can kind of create different haptic experiences. So, as you probably have already experienced during your winter school, our sense of touch is super important. So, if you want to interact with things in VR, feeling haptics, feeling objects, makes it so much more worthwhile, right? So, for example, training and education is an application area that we work on very much. So if you have doctors or dental students training, practicing certain procedures in order to get those fine motor skills in, they really need to have that feedback. Also for simulation, if you have simulation environments, adding haptics increases kind of like your decision-making skills. But then, of course, there are other applications like entertainment or cultural heritage where adding that sense of touch is super important. And my work, starts from this idea, what if we want to design a haptic experience? How do we go about doing this, right? So nowadays, if you have just a commodity VR system, you have your Quest 3 headset, what you're going to do is, from a very naive perspective, you're going to start programming some things on your computer, and then you're going to deploy that onto your headset. And then you're going to feel if what you've created is actually what you want it to feel like. And then usually for me, maybe it's different for you guys, but 99% of the time, just it doesn't work and I have to go back. So I'm kind of like sitting with my headset on my head and switching up and back until actually the experience that I've designed is what I want it to be. Um, so this entire design cycle is extremely cumbersome, right? You have to go inside a VR and then out of it again and then, realign your environment. It's also not intuitive. The one major problem is that kind of the language that you use for programming is completely different than the language that you use for touch. So it's a completely different world, but you're trying to express things in one way and then reach an outcome in another sense, actually. And it's also very individual. So it's very difficult to collaborate and to create haptic experiences. So in our work, we want to kind of like see, can we make this better? And we start from the idea like, okay, you understand what touch is in the real world. So, if I go out in the real world, I touch something, I can understand what this feeling is, what sensation it is. So can we take that understanding of the real world and place that in that process so that we create a little bit more intuitive design, right? So we can capture something from the real world or our understanding from the real world. And then can we bring those two worlds together? Can we create something, in VR for VR, or rapidly prototype things? And can we do this collaboratively? But can we also create better experiences that go beyond just these very simple vibrations that you usually feel? Right. So my work generally takes place in different areas of these things, and I'll try to provide an overview of different approaches that we've applied and to improving certain aspects of this design process. And as I mentioned before, there's a lot of stuff, a lot of work that I did on 3D printing. So the idea was can we 3D print structures that are kind of abstract in terms of the material that we would perceive, but they do have some kind of sensations of roughness or hardness. So the idea is that you have these low-level sensations of tactile perception that you influence those, but that the structure is actually more ambiguous. So early in my PhD, I started exploring different types of structures, and maybe you're familiar with these. These are hair-like structures that are 3D printed with a specific printer, and the real object is about 1 centimeter tall. Um, and the way that you print these is actually a different type of procedure. This is kind of like a voxel-based approach where you build a little staircase, what then ends up to be an actual kind of hair geometry to get these really, really fine details. Um, as you can see here, the structures then also are very bendable, and you can interact with them and feel different sensations. So what happens is if you make this kind of like hair-like structure longer, it becomes softer and smoother. If you make them shorter, they become a little bit more spiky. So they actually have a little bit of similar sensations than real hairs, right? If you have very, very short hairs, they feel a little bit more rough. And then the idea is, of course, to take those structures and print them and then put them into virtual reality. Now, as I mentioned before, we want these structures to feel abstract in terms of material, but we want to complete that perception by overlaying those structures visually with detailed texture information. So the idea is that we take those physical materials and we investigated different variations of these hair lengths so that we could kind of influence what the tactile sensations are of these structures. Um, and then by visually augmenting that structure, the idea is that you get really, really detailed textures on top that complete your material perception. And so we did extensive studies on this. For what we can see is that, on its own, these hair-like structures, these hairs, the length of the hairs actually reliably influence the feeling of roughness and hardness. So you can really design the tactile sensations that these surfaces provide. But then if you start combining things, um, you can recombine basically the tactile perception and the visual perception and kind of create very interesting sensations. So, for example, if you have a little structure that has very long hairs and that feels very soft and smooth, but now visually you see a kind of like a piece of glass on top, some people understand this to be a soft mirror. And this is something that we can't have in the real world, but we can now redesign in virtual reality. Um, or if you make them that same visual appearance of glass, you make that feel rougher, it becomes more broken glass. So people try to actively make sense of these combinations, but for us, it's interesting to see how we can kind of like redesign tactile experiences by recombining tactile and visual information. The big limitation, of course, that we have with these hairs is that they're not dynamic, right? They're very static. So you have to print out different structures with different roughness and hardness levels. So we wanted to explore, can we make this a little bit more dynamic? So then we started looking into kind of like metamaterial structures. And the idea is basically that you build your structure, your 3D printed structure in a certain way that it has a predefined behavior, right? So metamaterial, here you can see an example of like a shearing behavior. So if you 3D print the black part here in that shape, you can shear that material in a certain way. And we try to use mechanism like this to kind of create objects that would change its level of hardness and also its sensations of roughness uh, upon lateral compliance. So basically, you can see the different materials here. The more you press them together, the more features start popping up and the harder the structure becomes. So the idea is, of course, to complete that entire gradient of tactile perception and then reuse this in virtual reality. And then, we did more studies on this, and it turns out that this does help us to kind of complete the gradient in tactile experiences. Um, and then recently we started moving towards going beyond tactile experiences, right? So like, for example, what if you pick up an object in virtual reality? Can you give the sensation of um, hardness of the object? And so here you can see a 3D printed design that one of my PhD students is working on. And the underlying mechanism or the underlying idea is actually very simple. You have a basic structure that you can parameterize. So here you can see kind of like a spiral shape. And the more spirals are present, the kind of harder the design becomes. And the A version here is the softest one. So if you pick that one up, it really feels very soft. It kind of gets the softness of a sponge even. And then you can redesign, of course, the virtual environment as well. So if you pick up an object and you press that object, you hold the object, it will also visually comply. So then you can even go towards like designing the softness of grabbing objects in virtual reality. Um, but then, of course, the big question is how do you move from kind of physical touch experiences, things that we do in the real world and that we understand in the real world, and then transfer them to simulators or the virtual environments. So here you can see the example of palpation. So a doctor that palpates the skin of a patient to understand if there are any to make an initial assessment. Are there any conditions that they need to worry about? They need to understand the tactile perception to like a very extreme depth, and then creating those experiences in simulators is really difficult, right? You need to get all the details right. So one approach that we've been looking into is can you now capture something from the real world and then transport that into fabrication, right? To replicate things. So what you see here is it's a transparent silicone and it's coated with an aluminum reflecting layer. Um, and the object is being lit from the right-hand side off screen. And if you press the silicone onto a surface, you can visualize the stable surface deformations. So effectively, what this allows you to do is to visualize kind of like stable microsurface details, right? Um, and if you use this approach in a calibrated way, what you can actually do is you can take a very, very detailed texture, so like a piece of cloth or a piece of fabric, and then under predefined lighting, on the calibrated lighting, you can capture that surface information and you can create this kind of grayscale height map. So here, this grayscale height map that you see here represents like the physical deformations or the physical height up to like less than a millimeter scale. And you can apply that to a digital model as a surface, for example. And then effectively what you've done is you've taken a texture and you've replicated stable surface information of that texture. Of course, a lot of details are missing, right? So like you don't capture hairs, you only capture kind of like the macro roughness levels of that surface. But we wanted to see like using this approach, how far can we already go? Can we actually replicate also not only that surface, but also the tactile perception of that surface? Does it feel the same in a way, right? So we did this for a very wide range of textures. Yeah, so as you can see here, some are like visually they look very similar, but some are very completely different, as in the information that you can capture. So then once we capture this, what we actually see is that, you 3D print something and it creates this very big shift, right? So the blue circle here represents all these really detailed textures, and then they're very diverse in terms of how sticky that they feel, how soft that they feel, how rough that they feel. And these replicas, the green dots, they shift away from this blue set. And this is, of course, logical because, you know, we're printing something on plastic. So it becomes super, super hard. So that shift that direction. But what you can still see is that this kind of like green set is very, very diverse, right? So you can still create a very wide range in terms of roughness and also in terms of stickiness by replicating surface information. So if you now optimize your 3D printing processes for compliance, for softness, for example, you can bring those green dots closer to the blue dots. What we do see is that, you know, when people touch those textures, they're blindfolded, they don't see what it is, they just touch them. For a real texture, they would always, like most of the time, say that this is a fabric-like texture, right? But with these replicas, with these plastic things, it becomes very ambiguous again. They become like a wood-like or a stone-like or a plastic-like structure. So this again builds upon this ambiguity that we kind of want. So like if we put this back into virtual reality, then you know, visually you can complete that perception. So you can 3D print something and visually add more information to push people's perception in certain directions. And then the idea is, of course, you know, we build the perception of different materials from the ground up in a way. Now, of course, in recent approaches, because AI is becoming important, we also wanted to see, can we use, for example, a generative model to replicate tactile properties, right? We started from this variational autoencoder, and the idea was basically, you know, similar to stylization. You take an image and you apply a certain style to that image. Can we use this method of AI to apply the style of a height deformation? So what is actually happening here is that instead of you having access to a physical texture, you would just have a picture, you know, this brown picture of a texture. And our model tries to predict what the height or the height variations or the surface variations of that texture would be. Um, so the idea was actually just, you know, what if I don't have that texture, but now I take a picture of a texture? Can I kind of like try to understand what a physical version of that texture would be like? Turns out that that kind of works, you know, you can take a 3D model and then you can take a picture and now you can adapt, you can 3D print versions that are adapted both in different tactile variations, but also in different visual variations, which is actually quite nice because then um, you can explore different options or different tactile versions of a model that you would like to 3D print. Right? So again, yeah, we did this with different textures that we had and different approaches that we did. So the previous approach is the basic stylization method, and our method turns out to be more accurate. So effectively, what we could do is that you could take a picture of a certain texture, and then people expect that visual texture to have a certain level of roughness, and that would be encoded into the physical version. And then whatever predicted height map comes out of that, the hardness and the scratchiness would be something that would be put in there. So effectively, what you can do is you can create a pipeline where a designer takes a picture of a texture and they expect that texture to have a specific type of feeling. And now you can create a tactile variation or like a 3D printed version of that of an object with such tactile properties. So in our work, we show that, you know, you can create a diversity of objects with different use cases. Of course, if you deform such designs, then you have to make sure that, you know, they still stay functional. For example, here you see the little vase in B. We still need to make sure that the vase still stands upright, that it doesn't fall over, and so on. So that we have some optimization methods that ensures the functionality of the object is still maintained while the tactile properties and the visual properties are actually deformed. Now, if we take a little step back to kind of like prototyping haptics and then looking at kind of like commodity virtual reality hardware, then usually yeah, vibrations are designed as waves, right? So if I would program a vibration for my controller, I would think about it in a sine wave where I'm going to adapt how strong, what kind of frequency that wave has, what the amplitude is, and how long I am sending that signal. If you think about that for a while, then it's very unclear to me, at least, how what a vibration would feel like. Imagine that, I have a controller, the controller is vibrating, and now I say like I need to increase the amplitude. How can I optimize this process to say that it needs to feel like a texture, right? That's really complex because, this language of using a vibration is not a language of touch that we actually use. So in our work, what we do is we rely on different types of concepts to see can we kind of have a better understanding of how to design and a better language for touch. And one of the things that we start from are these two shapes. Maybe you know them. One is called Booba and the other one is called Kiki, right? And I'll let you guess, think about it a little bit which one is called which. So if you see the shapes, they have certain features. Um, and if you hear the sounds, we associate those sounds with certain features. So the left one, the more round one, is called Booba. Usually by ni more than 90% of people would assign Booba to that shape. Well, Kiki is the one on the right because it has more sharp features. So this is an example of a cross-modal correspondence, as what we know, because there's a correspondence between sounds that we perceive and visual information that we perceive. Um, and then this is heavily used in like in media, for example, in comics where you have onomatopoeia that try to kind of like make that experience more immersive, right? So here you can see the word tang. It is kind of saying that, something is being shot, but it also carries kind of like a material experience with it, right? That word patang together with the can being shot gives you the impression that it's like real metal. And um, we try to rely on a concept like this to see can we use this for design. So we started building kind of like a framework for virtual reality where a person, a designer, can design what an object should feel like. Vroom, vroom, vroom. And this is where the sound would come in. I hope that you heard it. If you
Yeah, we
didn't
hit.
hear
It's
it,
fun. That's great.
that's
Thank
great.
you. Yeah.
Yeah. So the idea is that the designer picks up the object and now tries to vocalize what that object should feel like, right? So the framework captures the audio signal that you can see here, and then also provides ways to kind of like adjust the certain parameters of that feeling. Um, and the idea behind that is, of course, that we did studies on how do people verbally express certain tactile impressions that they have. And then we used those design guidelines to create a framework now allowing people to very quickly and rapidly prototype experiences. So one thing that now the designer can do is to create very easily haptic illusions, right? So you pick up an object and she verbalizes something like tonk, tonk, tonk. The idea being that there's some kind of object rolling around or tumbling around inside that object. And by refining the parameters of that vibration, um, then you can actually change kind of like the perceived size of the object or the perceived amount of objects rolling around inside the box. Um, and we also looked into kind of like, can we now create very diverse sensations that are a little bit more complex to design in a normal fashion. So here you can see the designer is um, using kind of like a slider going over a metal bar that has different visual features. We asked participants to design different parts of that slider. So the idea being that one part is more rough than the other part. And they can do this with one vocalization. So the idea is that, they just express it once And now different parts of that object have been designed, and you kind of scroll over that audio to make sure that the audio or the vibrations are aligned with the experience that they've designed. Um, yeah. So using this method and this approach, we can see that you can very easily create haptic illusions. You can also use multi-layered designs so that you can kind of design what an object feels like, for example, when it's on versus when it's off, and also that you can then feel that it gets more intense when you use it, when you swing the sword, for example. And these positional mappings are usually things that are really difficult to design, where, for example, here you have a drawer. If you open this, when you reach the end, you want to feel kind of like the end hitting something so that you can't open it anymore. So with this method, it allows you to very easily express those tactile experiences that you go through. Um, and then we started looking into, because haptic design is very individual and is also kind of more offline, how can we create kind of like more interactive ways or more intuitive ways to design more complex experiences? So you can see one device that we built that has 8 actuators actually. The idea is that you can attach them onto your body to provide vibrational feedback on your skin, but it uses kind of like a playful music metaphor to create experiences. So it has this kind of like more piano-like approach that you can press the buttons and you record a pattern, and you can share that pattern with other people as well. And in the more recent version, we looked into kind of like a more portable version of this that also supports more different input mechanisms. So this was a project that where we had the idea like, you want to design complex tactile experiences, maybe for on your body. And now I want to make sure that I can change the input device. It could be a keyboard, it could be a controller, or it could be actually a musical instrument that you connect to the software, and then you design experiences in a more playful manner. So you can see that like one of the things that we allow people to do is record these experiences, edit them afterwards. We have kind of like a versioning approach. And then the nice thing is that you can share that with other people so that you can actually create a very simple design that other people can also experience. But the output device doesn't need to be the same thing. So you can connect it to different output devices as well. And our study looked into, what if you want to design an experience? Can we also do this collaboratively? So here you see two designers working together to create an on-body experience, the one that you saw at the beginning, like stroking somebody's arm. So first they discuss where does the placement of these actuators happen. Then they start kind of like explaining to each other how what the sequence should be, what the intensity should be, and they can play around with trying out vibrations like this. And then the thing is that when they are recording, everybody that is connected can feel what is happening. So we can design together. And so the metaphor that we're trying to go towards is similar to how we would make music in a band. Can we now make vibrations in kind of like a vibrational team? So everybody has an instrument that they work with and kind of like builds towards that full experience. And from our studies, we see, that we compared people working together in the same room or working remotely, and we see that people use different types of language to communicate with each other. They use objects to kind of like explain what they are aiming to design. And it also allows them to be very playful and exploratory in their designs, right? So they do more, they explore more things that they can do because now they have the tools to prototype things very rapidly. Yeah, and then kind of like going towards vibrations, question is, of course, how can we utilize those vibrations to create experiences that just go beyond picking up an object in VR and go beyond just a basic vibration or a notification? Can we create uh, more complex perceptions? So, and my postdoc, she has been working on sensory substitution. So the idea of sensory substitution is that you have you take information that is usually provided in one sensory modality and you apply that in a different sensory modality. So there are different examples that already exist in literature. This is, for example, a haptic vest that is vibrating based on external sounds. So it's capturing audio from the environment and then displaying that through haptics, right? And this one is using where the user has a camera and is applying vibrations onto the tongue of the user. So the user can now kind of like go around their environment and feel the shapes of objects around them on their tongue and vibrations. Um, and then, yeah, so there are different investigations onto what the correlations between different sensory modalities are. The Stopa speech system kind of investigates what is the relationship between kind of visual height of an object and the perceived musical note or the frequency of a sound, and then over time. So it turns out that these cross-modal correspondences that I talked about before can actually be used in sensory substitution so you can convey information in different senses. And um, so yeah, as I mentioned before, my postdoc, she's been working on mapping out this space very much. So she's been looking at devices that exist and where are gaps. And there's apparently a lot of opportunities. So she tried to understand like how much if you look at these devices, how much do you need to learn these methods, and do you mask the original sense versus the other one, and which ones can be mapped on which ones? Um, but what we did in our work is to think about the perception of localization. So imagine that you hear a car pass by and if your hearing is intact, you can very easily recognize where that object is, right? And you do this in different ways. So, for example, each ear receives the sound at a different kind of like intensity level. There's also kind of a phase shift going on. So, like one ear hears the sound earlier than the other ear. And if you use your head motion, then you can kind of like sample the space a little bit more and you can understand where objects are in a very detailed accuracy. So we tried to transfer this to haptics, right? So the idea is, can you hear or can you localize an object through vibrations? For this, we built kind of like a method where the intensity of the vibration is in your controller is linked or connected to the location of an external object. So now you can feel objects around you and you can localize them very rapidly. In order to do this, so what we did is the two methods that we tried to explore. One was on using a direct ear metaphor. So basically, your controller on your right hand is kind of connected to your right ear. And if you would kind of move your head or twist it a little bit, then you can kind of feel where that object is by kind of listening to it. This one was perceived to be rather complex by users because you kind of have to like move your head, which is not directly related to your hands. But the next approach, where it's kind of like a direct coupling between the vibrations in your controllers and the distance from the controller to the object seem to be very, very intuitive. So effectively, you are kind of like having tactile ears in your hands, and you can localize objects around you. So we did this, we did like a study or several studies where there are multiple objects around you, and one of them is kind of making vibrational sounds, and the user has to kind of localize which object is creating those vibrations. It turns out that if you do this, that people are actually very accurate in this. They are of similar accuracy as like localizing objects through sound. So it shows that you can transfer existing kind of like abilities in a certain modality to other modalities, and especially the tactile approach. There is still kind of like a front back confusion, as in like if something is right in front of you or right behind you, the vibrations make it a little bit difficult to understand where it's coming from. But yeah, we also presented a little game around this. So the idea is that you have a bunch of objects and you need to be super fast into finding the blue sphere. But while you're searching, you're actually feeling the location of that object through your controllers. So you kind of intuitively know, is it to the left of me or is it to the right of me? And it turns out from our demo that people are on average without vibration, it takes like 4 seconds to localize the object. Well, if you add those vibrations, it only takes about 3 seconds. So just adding this extra sense in a way kind of makes people definitely more accurate in localizing things. Another approach to improve haptics in commodity experiences is to think about can vibrations actually provide forces, pseudo forces. So if you would like to design kind of an experience like this in virtual reality where you pull a bow and you actually feel that the bow is pulling, this is not easy using normal controllers. Usually we would, have a method that applies actual forces. So we try to explore pseudo force application. So uh, giving people the impression that a force is being applied. And in order to do that, we kind of used the idea of asymmetric vibrations. So if you have this, as you can see, this actuator on top here, it's kind of like a pin moving up and back. And usually those vibrations that this pin provides are very symmetrically moving. But turns out that if you asymmetrically move that pin, so that kind of like moves to one side only, it gives a little bit of sensation of a force being applied. Um, the problem is that in order to apply very strong force sensations, you need to increase the amount of vibrations, but then you get the impression that there are more vibrations being applied than forces being applied. So this gives like a little bit of contradictory statement where if we do increase the power, it's not achieving the result that we want. So we use the concept of sensory attenuation. So if you scratch your own arm or somebody else scratches your arm, you will have a different perception, a different tactile impression of what is actually going on. So if you self-generate your stimuli, it's perceived to be weaker. So we ask the question, if you now are the cause of these forces being applied, would you perceive the vibrations to be less than the forces to be more? Turns out that actually works. So if you motion couple those vibrations. So basically, you would couple those vibrations based on the action that the user is doing. It turns out that you can create really realistic pseudo force sensations. And kind of our work exemplifies this by having, VR experience where you pull a bow and you actually feel that that bow is being pulled, or you pick up an object and actually feels heavier just through vibration, so no visual manipulations or actual forces being applied. Or two magnets, so you're holding two of those actuators and you visually see two magnets, and it gives a very realistic sensation of um, uh, holding two magnets that are pushing each other away. So it turns out that different methods are, of course, better for different experiences, but generally, if you motion couple things, so like if you actuate vibrations, or if you actuate vibrations based on the movements of the user, you can create better experiences. And then I want to look a little bit further beyond tactile experiences. So during my PhD, I also explored kind of like different approaches to visual haptic integration. So how can we build different types of haptic experiences in virtual reality? And one of the things that we explored is this idea of walking in virtual reality, but one thing that is super important while walking on different floors is the sensation of slipperiness that that surface is providing. Um, so our idea was very simple. Like, what if you just added texture to the bottom of your shoes? And would different textures provide different experiences while walking? Um, so we looked again at all these textures that we had lying around, and then we tried to classify them in a very hanky way to like see how slippery are they. And then we built this study where people would wear shoes with different textures applied at the bottom, and then visually they would see different surface materials. Then turns out that actually you can create a design guideline or like a design approach where you kind of classify the slipperiness of a certain texture, and then you can predict which environment would be the best for that certain texture, or vice versa. If I have a virtual environment and I want to design a realistic experience, I can classify certain materials and then predict like which material is the best for that specific environment. So by using textures, off-the-shelf textures, and then putting them underneath the soles. Another approach that we looked into is the concept of using these dynamic tactile experiences, but then for different passive haptic experiences. So here on the left side, what you see is a person holding like a custom-built controller um, that has a certain center of mass. And on the right-hand side, that the center of mass of that object has shifted forward in order to give the user the perception that the object has become heavier. And as you can maybe see, the ideas of a fishing line, that you're fishing in virtual reality and I'm capturing a fish. But the moment that you capture that fish, you want to have the sensation that the fish is actually pulling you away, or that it's heavier, that it's actually on your line. In order to do this, in our method, what we do is we kind of try to use the user actions to reconfigure the device. So while the user is kind of interacting with their device, we've used visual manipulations to make them reconfigure or put the device in a certain state. And then by using also a visual remapping, they are reconfiguring this object to make it feel that it's heavier. So this is going a little bit more into the direction of like passive haptic feedback, but then the 3D printed version of that. And then a kind of like a last approach that we worked on is to apply thermal motion. So imagine that you would like to build an experience in virtual reality where you have the feeling that there's steam coming over your body. For example, you're in a sauna. Um, we use kind of like the idea of apparent motion to create a realistic sensation. So apparent motion is this idea that if you have actuators, that are spaced out on your skin, for example, these tactile vibrations, if imagine that you only have four of them, but you want to give a continuous sensation, you need to interleave the actuation in a specific way, in a very time-controlled manner to give the idea that there's actually something rolling over your skin. And we did this with thermal sensations. So by combining a very designed thermal actuation with a visual experience, we can actually now create a thermal experience that is very realistic and provides kind of like the perception of steam over your body. Now, where do we go from here, right? First of all, um, the idea, usually the approach that I've taken in the past is always, I want to design something, I want to print something, and then I investigate, okay, how do people perceive it? But actually, we want to do the inverse, right? So we want to I want to say this is what my experience needs to feel like, and whatever printer I'm using or whatever vibration device I'm using, it just needs to figure it out, right? So we're working towards this idea of perception-aware design, where a designer can say, I have my virtual experience, I want my floor to be soft, and I want my object to be heavy. Um, Figure it out. What is it what I need? Um, Yeah, and then this also needs to create kind of like an output independency. Usually, in my work, I've looked at either using 3D printing or using vibrations. But in the end, what we want, of course, is this vision or this idea of virtual reality being this universal immersive experience that we can just, regardless of what output device that you're using, provides the experience that the designer intends to create. And in order to enable that, of course, we need to provide people with the tools or the software, so on, to create those things. So with that, this was my talk. If you have any questions, I'd be happy to hear them.